Okay, we're recording the revolutions versus time, trying to get a handle on the coefficient of friction, or at least on the effect of friction on the system. So it's fairly easy to do that. I'll set one in motion when we have a little slack time. Anybody who's not here gets to make their observations from the video. Okay, now what happens at the end? Let's just see what happens when this thing finally comes to rest or doesn't come to rest. Okay, here we go. Not sure it's going to get an extra oscillation, but there it goes. And now what's going to happen? It's oscillating. And there's a question whether this is simple harmonic motion or not. Now, the way the thing's flopping around on the axis, not totally clear. But the question is this a simple harmonic motion? It's an angular simple harmonic motion. It has the characteristics of angular simple harmonic motion. What are the characteristics of angular simple harmonic motion? What are the characteristics of simple harmonic motion in general? Okay. Now we haven't talked about it. We haven't talked about regular simple harmonic motion, but the mass on the spring, the stuff we've done with the energy of a mass on the spring, is totally analogous to the energy in the motion we have here. And we'll make that analogy in class. Right now, the thing we would want to do is time these oscillations. If we really do have damped simple harmonic motion, the oscillations ought to be relatively constant in time. In other words, the angular frequency of the oscillation, or the frequency of the oscillation, ought to be pretty much constant. And of course, we have a class full of people who know enough differential equations to solve the differential equation for damped simple harmonic motion. I'm not going to ask people to do that. I'll do it for you. You'll understand what's going on. So it's still, is it still moving a little bit? I think so, but maybe not. It's pretty much died. No, we're going to actually use Audacity to get data on those oscillations. Okay. Now we're going to observe oscillation. So let's start it a little bit fast. We'll probably go through a couple of revolutions before it starts to oscillate. Here we go. Okay, I believe it's not. What I should have done, for the sake of anybody who's looking at this from someplace else, is get this thing at pretty much a perpendicular to the line of sight of the camera. It still wouldn't be great. Okay, that's a little difficult to get the positions off the camera, but we want to do the best we can. Okay, so we've got that. Okay, well, now I'm gonna give the thing a pretty good spin, and we're gonna time it. Every time it returns to a certain point, we're gonna time complete revolutions. So if you're watching this in camera, just figure out how you're gonna tell when it's completed a revolution. Okay, could be when it's at the bottom of this thing facing you. Could be when it's level, whatever you think. Okay, here we go. Okay, I'm gonna let it complete the oscillation. We don't need to take observations, but if you're watching this on video, do. Also, I recommend that when you take your observations, you don't listen to the clicks that were made here in timing. Okay, in other words, mute the sound. So you do your own independent observations. Although, you know, there's not going to be a huge amount of difference, even if you were listening to the clicks, but we want independent observations. Okay, when this thing stops, we'll stop the video. In the meantime, next task is going to be some thread. We're doing that with machine. We're going to use the same masses that we used when we did the Atwood machine over there a couple of weeks ago, a month ago. Okay. So hopefully you have your lab data and know what masses we use. You better kind of repeat it for this one. Okay. Now I think, okay, I think it's done. Okay, well, we've got an Atwood machine thing going here. You probably see weight on this side and paper clips and the magnet don't interact very well. Well, thought I had it. Okay. Oh. Okay. I can't see on the camera what I'm doing. Probably a good thing. I want to be held responsible. Okay. How many paper clips did you have on there? 3? I'm sorry?
I think there's 4 right now.
Okay, I think we've got to modify this system. It occurred to me that the paper clips would be the problem that they are. But what we just observed was that this system was undergoing something very much like simple harmonic motion. Doesn't seem to be doing it now. Somehow the balance has been messed up. Of course, I was in much fun with it. Not ordinarily balanced, what's going to happen? And now we are getting a pretty good simple harmonic motion. I just think when I upset it, I'm on one of the neighbors or something. So can we do this? Yeah. What we've got here appears to be a much smoother, simple harmonic motion. Assuming it's simple harmonic. It's probably much closer to simple harmonic. So let's go ahead and time it. Tell me when you're ready. Okay. 1, 2, 3, release.
That's all we get done.
I'm still detecting motions. We're gonna let it go until it stops so that people that are missing today can continue the trend. I think it's pretty much stopped, but let's be sure. Okay. Now we've got a problem. That should be 30.4 centimeters. Either 2 foot. Noise. Okay. Okay. The wrap before the last one was when the hanging weights hit the ground. Okay. I'm just going to rewind this. So I want this way. There it is. Floor. I actually want it on the floor when this small magnet is here. Okay. I'm not going to rewind it the wrong way. Through 1, 2, 3, 4, 5 revolutions. And I'm going to signal when I start and when this system of masses reaches its floor. We might end up with a collision here. We'll see. Slow it down. Okay, I didn't tell you when I can't see. Ready? Set. Release. Stop. That's not everything. I shouldn't have tried to stop the rotation. There's an equal and opposite reaction to the force I exerted to stop the rotation, which destroyed the whole system. Anyhow, we want to get the angular acceleration and more information. Okay.